Hello dear students, welcome to Experimental Techniques and Material Characterization lecture number 32. I'm Dr. Farwez Ahmad. In this lecture, we will continue our discussions on Raman spectroscopy. This is the part number third of the lecture series on Raman spectroscopy. In these lectures, we will differentiate between Raman spectroscopy and infrared spectroscopy, that in short we call FTIR. So let's proceed towards the detailed differences between the Raman spectroscopy and IR spectroscopy. So what is the key difference between the Raman spectroscopy and the FTIR, or we can say the IR spectroscopy? So we remember the Raman spectrum results from the scattering of the light by vibrating the molecules, whereas the IR spectrum results from the absorptions of light by vibrating the molecules. I mean, this is not the one difference. There are a lot of differences, so we will discuss them one by one. Now, in Raman activity, it's basically occur due to the change of polarizability of the molecules, whereas IR activity occurs due to changing dipole moment. I mean, Raman's activity basically occurs due to polarizability of the molecule. In comparison to that, high R activity occurs due to the changing dipole moment. So here you can see the example. I mean, that's what happened in the Raman activity and what happened in the IR activity. So in Raman spectroscopy, we normally taking the imaging. In that we have monochromatic light of high intensity laser beam that can be used in IR, UV or visible region. I mean, we have high intensity laser light. So that laser light we can use in IR, UV or visible regions. But unlike that, in IR spectroscopy, the light range is limited only to the IR frequency. So this is also one of the key difference between the two spectroscopy. In Raman spectroscopy instrumentation, scattered light is observed at right angle to the incident beam, while if we consider that in the IR spectroscopy, so in IR spectroscopy, the absorption signal is estimated in the same directions as the incident beam. So the technique of Raman spectroscopy is non-destructive. What it mean? It means that sample measurement can be done directly in a glass containers. So in the case of pharmaceutical samples, they can be measured directly in the sachets. Whereas in IR spectroscopy, it needs sample preparations through the potassium bromide pellets for observation of gels, film, and the liquid. So here you can see in the spectrums, I mean the comparison of both the spectrum, the IR spectrums and that Raman spectrum. So the Raman spectrum you can see it here in the blue, whereas in the black you can observe the IR spectrum. So you can observe both the spectrums in detail. So you already know about the Raman spectrum. The FTIR spectrum we will discuss that in the coming lecture series on the IR spectroscopy. So Raman spectrum is the result of the Raman spectroscopy, where a laser is used to analyze the sample due to the inelastic scattering of the photons and the sample. Whereas IR spectrum is the result of IR spectroscopy, where IR radiation is utilized to analyze the sample. IR spectrum is based on light scattering, whereas Raman scattering is based on the light absorptions. So vibrational modes are active in Raman spectroscopy if they cause a change in polarizability. Vibration modes are active in IR spectroscopy if they cause change in the dipole moment. So the main concept you should keep in mind is about polarizability, and the second thing is the dipole moment. I mean, this is the key difference between the Raman and the IR. One is based on the polarizability of the molecule, the other is based on the dipole moment. So Raman analysis can use water as a solvent, whereas IR spectroscopy cannot use water as a solvent. Raman spectroscopy is a highly expensive method, whereas IR spectroscopy is relatively inexpensive. In Raman spectroscopy, laser sources are highly intensive. It facilitates focusing the beam on a small sample area with a small volume. So, when the quantity of sample is limited, this facility serves as a primary advantage. So, a higher degree of amplification of weak stock signal is a requisite, and the presence of intense relay light scattering. The situations we have already discussed in the previous lecture, but here you can also you can also see for yourself the different vibrational you can see the vibrational energy state, the ground electronic state, and you can also observe the infrared absorptions, relay scattering, stock Raman scattering, and anti-stock Raman scattering. We have already observed this kind of situation in the previous lecture. So this result in higher cost for the analysis when compared to the IR spectroscopy. However, the higher cost can be easily justified against the benefit offered by the Raman techniques. So in Raman spectroscopy, band present below 400 per centimeter can be measured, as the scattering effects are usually weak. So Raman spectroscopy exhibit low sensitivity at times. So sometimes visible light excitation, fluorescence, and contaminations can overlap with the signal. So observation of the Raman spectra will be decided by the polarizability of the molecules. For observation of the IR spectra, the criterion is presence of the dipole moment and the molecules. So the Raman spectrum can be recorded at a single exposure, whereas two separate runs are required with a different prism to cover the whole regions of IR. Water is used as a solvent for the Raman spectroscopy, while water cannot be used as a solvent for IR spectroscopy, and the reason is because it is opaque to the IR spectroscopy. Raman spectroscopy is very accurate, but not that much sensitive. IR spectroscopy is both accurate and sensitive. In Raman spectroscopy, optical systems are made up of quartz or glass, while in IR spectroscopy, optical system is composed of special crystal like sodium bromide or uh, calcium fluoride. Occasionally, photochemical reactions occur in the region of Raman lines and create difficulties for the Raman spectrums. In IR spectroscopy, photochemical reactions do not occur. So, in Raman spectroscopy, substances to be investigated should be colorless and pure. Since Raman lines are weaker in intensity, concentrated solutions should be used, and increasing the intensity of the Raman's line, whereas in the IR spectroscopy, dilute solutions are prepared for measurement. In Raman spectroscopy, vibrational frequencies of larger molecule can be measured. So in the case, unlike that, if we consider the IR spectroscopy, so in the case of IR spectroscopy, vibration frequencies of larger molecules cannot be measured. So, homonuclear diatomic molecules are found to be active in Raman spectroscopy, whereas in IR spectroscopy, homonuclear diatomic molecules are not active. Raman spectroscopy calculates relative frequencies in which the sample scatter radiations, whereas in IR spectroscopy, it's evaluate absolute frequencies and with the sample observe the radiations. Raman spectroscopy is used to homonuclear molecular bonds. It is able to distinguish between the single, double, and triple bond between the carbon atom. So unlike that, IR spectroscopy has responsiveness with regard to the heteronuclear functional group vibrations and polar bonds. An example is OH stretching in the water. So, in sample preparation, Raman spectra analysis has no requirement, but IR spectroscopy has constraint of the thickness of sample, uniformity, and dilution for avoiding the saturations. Fluorescence will interfere with the Raman imaging, but it is not an issue in taking an IR spectrum. Both the method have some limitations when taken separately, but when used combinedly, they become a powerful tool in material characterizations. Both can be used with microscopic techniques. Raman spectroscopy is a weak technique, while IR spectroscopy is a stronger technique. Molecule with a function group having strong dipole display a strong peak in IR, whereas molecule with a function group possessing weak dipole readily alter and polarizability, manifesting strong peak in the Raman spectrum. Raman spectroscopy furnishes data about intermolecular vibrations. I mean, here you can see and intramolecular vibration and intermolecular vibration. I mean, here you can see, you can differentiate I mean for yourself. And here we have take the case of the carbon dioxide. So intramolecular vibration displays specific vibration of the atom in a molecule, and thus helps in identifying a substance. Intermolecular vibration provide informations about lower frequency modes, which reflect crystal lattice structures and polymorphism. IR spectroscopy probes the fingerprint region uh, of the region. Intermolecular vibrations are highly characteristic of bonding of atom as they are well defined. In the investigation of the crystallization process, Raman spectroscopy analyzes solid crystals, form, and solutions, whereas IR spectroscopy is utilized for solution phase supersaturation study. Raman spectrometers have laser light source operating in the near IR or visible regions and the electromagnetic spectrum, whereas IR spectrometer possesses black body radiations providing energy in the mid IR regions. Raman's spectrometer have holographic grating with the CCD detectors, whereas IR spectrometer uses interferometer providing modulated radiation, which is detected by photonic detectors, photoelectric detectors. So that's all we have for the differences between the Raman and IR spectroscopy. Hope majority of you might have understood the differences between the Raman and the IR spectroscopy. So that's all we have for this lecture. But stay tuned for the next lecture on Raman spectroscopy. In that lecture, we will have a discussion on the instrumentations, mode of vibrations, and type of Raman spectroscopy. So stay tuned for the next lecture. Till then, bye bye.